Okay, so thank you, Andy. Thank you to all the organisers for what I've seen so far as a great meeting. I'm very sad not to be there, and also sad because of the time difference that I'm not attending as many talks as I'd like to. Okay, anyway, just to get started, there's some references here that relate to the sort of overall structure, really of the 3 talks that I'll be giving in total. So, and as I go along, I'll give other sort of more relevant references at the time. Okay, so of which the only thing to read on this page is the 2 relevant things. One is this article by Sean Curry and myself, which is a sort of overview of many of the tools that I'll use in the first couple of lectures. And then today, what's closely linked today is this, or the second half of today's talk is this article with Peterson, which has been sort of in development for a long time, but is finally appearing this year. Maybe it's already on the Maths.net, I think. Okay, so let's get to the start. And do let me know if you can't hear well or anything, because I'm having trouble hearing your end, but I think it's okay in the other way. Okay, so up here I've got a picture. I hope it's clear from there, but this is supposed to, this M here is supposed to be perhaps some sort of infinite space, like a complete non-compact pseudo-Riemannian manifold. So one of the questions that comes up is to do with compactification, namely, can we add some sort of boundary to this infinite manifold as a boundary of infinity and then sort of exploit that? And of course, as most of you will know, the answer is yes in many cases and so on. So we're going to talk about conformal compactification starting on the next slide, but I just wanted to mention some keywords that come up linked to this, and these are things that have already been mentioned before. One is the Q curvature. It can be defined in using this sort of setting. More recently, we've discovered some sort of higher Willmore energies and invariants. And these are actually related to Q curvature. So these higher Willmore energies actually generalize the Q curvature. So I'll explain that in tomorrow's lecture. And these are all linked to renormalized volume of such things, and the calculation of volume anomalies, for those of you who know what that means. Otherwise, we'll touch on it tomorrow. Something in this context, a special case is Poincare-Einstein manifolds. And then these structures are used for scattering and various PDE boundary problems in physics, the ADS CFT program. And from our point of view, the origins of this sort of program, as mentioned in Mike Eastwood's talk, is the sort of Fefferman-Graham program, where you try to study conformal geometry by studying a simpler geometry in higher dimensions, in a sense. And then in physics, the idea of holography actually dates back to 't Hooft, at least according to Wikipedia. But the version that we're interested in is sort of most famously popularized by Mulder-Sena and many other names. Okay, so let's get on with the talk. So that's all sort of background. So we're going to be talking quite a lot in all 3 talks about what we call a conformal compactification. So let's be careful about what that means. We're going to do it just in a limited sense here, so we won't be talking about the most general situation. But we have a pseudo-Riemannian manifold, which you should think of as being complete. I'll allow it to have signature. So you would say that this pseudo-Riemannian manifold, which will be a complete manifold, has a conformal compactification if it's the interior of a manifold with boundary. So the original manifold is going to be the interior of a manifold with boundary, and I'm calling M bar the manifold with boundary, such that, so this has a pseudo-Riemannian metric, but on the manifold with boundary, you want a metric that goes to the boundary. Okay, so this G bar is a metric right to the boundary, and it's conformally related to this original metric in the following sense. The original metric, which I'm calling G plus here, is R minus 2, R to the power minus 2 times this metric that goes to the boundary, where R is a defining function for the boundary. So that means that the only zero locus of R is the boundary, and everywhere along the boundary, GR is nowhere zero. Okay, so that's what we mean by defining function for the boundary. Now, of course, this means, so G bar goes to the boundary, there's R to the minus 2. So where R is 0, this metric's singular. So, of course, so the boundaries are at infinity. Now, what you canonically get here is a conformal structure on the boundary. To see how that arises, what you should be thinking is that this metric G plus is fixed. Nothing else is fixed. All you know is that all you need is there exists such a G bar. So you can change your mind about G bar and R simultaneously. So for instance, you can replace R with a positive function times R, and you'll get another defining function for the boundary. G plus is fixed, so you should conformally rescale this G bar to compensate for that. And then each G bar that you get induces a metric on the boundary, but then under these conformal transformations, you just get a conformal structure induced on the boundary. So that's the way that a conformal structure arises on the boundary in this picture. And so these have been used as tools to link conformal geometry to pseudo-Riemannian geometries and so on. In these talks, I'm going to say it's Poincaré-Einstein if this interior metric's Einstein. Now, usually this term's restricted to the negative Einstein case, especially in Riemannian signature, but just to be simple, I'll just say that it's Poincaré-Einstein if this metric's Einstein. And throughout these talks, D is n plus 1, so I'll mainly talk about dimension D, which will be n plus 1. Okay, well, let's just go back. So we want to study these things in some detail. Now, this structure is not exactly a Riemannian manifold with boundary, obviously, and it's also more than a conformal manifold with boundary. So we want to understand how to treat these sort of structures. And in particular, so away from the boundary, it just is a pseudo-Riemannian manifold. So we really need to understand the geometry at the boundary. So today's talk is going to we'll do a first step in that. And the first step will be to treat the whole thing as just a conformal manifold with boundary. Okay, so to understand that boundary, we'll think of it as a hypersurface in a conformal manifold. So we're going to study hypersurfaces, and that's the sort of first part of today's talk. And yeah, there's a second part I'll come to. Okay, so what do I mean by a hypersurface? So I mean it's a codimension 1 embedded submanifold. So whether you're in a Riemannian manifold or a conformal manifold or whatever, a hypersurface just means that. Now, one of the reasons that they're important, and here's some supposed pictures of hypersurfaces, I'm calling them sigma. One of the reasons they're extremely important is, for instance, if you have a domain, then the boundary of the domain is a hypersurface. If you have a manifold with boundary, then the boundary, from my point of view, is a hypersurface. So I'm going to think of the boundary of a manifold with boundary as a hypersurface. You should extend the manifold a bit and so on to really make that precise, but we'll just do it simply here. Okay, but because they arise as boundaries in this way, and also, of course, as foliations, but let's focus on the boundary case, they're important for PDE boundary problems, in physics and in mathematics, and also in representation theories. So in various homogeneous settings, you have a manifold with boundary and different groups acting on the interior versus the boundary and so on. Okay, so we want to understand how to treat the geometry of such hypersurfaces. And in particular, what if this hypersurface is the boundary of infinity of a conformally compact metric? We just talked about a conformally compact metric. So how do we treat that hypersurface? What if instead, and this is a sort of weakening of the question, if you like, or more general, is if we think of this hypersurface as just sitting in a conformal manifold. So you now just have a conformal class of metrics. And that conformal geometry has been mentioned before, but I'll revise that anyway. Okay, so in these settings, some sort of obvious questions are, how do you make invariants? And how do you make invariant operators? So this is already complicated, especially if you try it naively. So we want to look at those questions first, just for conformal, especially in this setting. So we have a hypersurface and a conformal manifold. How do we make invariants of that, and how do we make invariant operators? Okay, so let's revise conformal geometry. It was mentioned a bit in Andy's talk. It was mentioned again in Mike Eastwood's talk, and touched on in Jan's, and probably others. I think many others. So a conformal manifold, and it's going to be dimension D, as I said, which will be at least 3. So it's a structure of a D manifold equipped with an equivalence class of metrics, and I'll allow them to have signature PQ. So the equivalence class is just by multiplying by a positive function, and as usual, the convention is you take the square of a positive function. So this was the notation that Mike used. I will mainly use a variant of that, but which he also used. But that's the usual setting. Okay, now on a conformal manifold, because there's no distinguished metric, it turns out that density bundles are important. And again, Mike Eastwood mentioned that this is the case, so let's just remember that. So how do you define the density bundles? Well, the answer is they're already there. I mean, you just have to give them names, really. So take the tangent bundle, it's got rank D. Take its top exterior power, that's then a line bundle. If it's an oriented one, if the manifold's oriented, but if otherwise, if you square it, this is an oriented line bundle. So we normally square it to make sure we have an oriented line bundle. And then we write curly EW for the roots of that line bundle. So these are line bundles that are roots, and the convention is such that this original line bundle, this one here, has weight 2D. You know, so you have general weights for W being a real number. And the convention is then when it's W0, this is the trivial bundle. Of course, it is the trivial bundle then. Okay, and then we put a plus for positive elements. We're not going to use that notation much. I'll put, for any vector bundle, if I put a W, a weight beside it like that, it means that vector bundle tensored with one of these density bundles. Now, with all this notation on a conformal manifold, you don't have a metric, but you do have a conformal metric. So this was also mentioned in Eastwood's talk. So this is also a symmetric covariant 2 tensor, but now it has weight 2. And the existence of this is just tautological nonsense in a sense from the structure. So on a conformal structure, you have that thing. There's ways to talk about that, and I've indicated those down here, but I'm just going to, for this talk, just say it's there. And we're going to use that, like in Mike's talk, to raise and lower indices. So then you get weight changes. Okay. So what is our problem now in this language? So we want to understand hypersurface type submanifold embeddings. So sigma has dimension n, it's going into a dimension n+1 manifold with a conformal structure as an embedding. And we want to understand things like, what geometry is induced on sigma, how do you construct intrinsic and extrinsic invariants of this embedding. Standard sorts of questions, the kind of first steps you would take if you were trying to understand this. So how do we construct, for instance, the conformal invariants of sigma? Perhaps you would like to try and make all of them. That would be a good idea. That's very hard, but we can at least indicate how to get going. And then the next thing is, how do we construct and understand conformally invariant differential operators along sigma? Now, there's a lot of things we could mean by such differential operators, and I'll talk about some examples. Now, to keep life moderately simple, I'm going to restrict to hypersurfaces that have the property that any conormal field along the hypersurface is nowhere null. So this is the usual way of saying that the hypersurface is non-degenerate. Now, what happens in that case is that the restriction of any metric from the conformal class induces a metric on the hypersurface. This is the first fundamental form, sometimes it's called, or less grandly, just the induced metric. And so looking at all the metrics in the ambient conformal structure, the ambient conformal structure induces a conformal structure on sigma. right? Because for each G, you get a G bar, and then a conformally rescaled G, you get a conformally rescaled G bar. Okay, so the ambient conformal structure induces a conformal structure on sigma, provided the hypersurface is non-degenerate. Okay, then in this setting, in Riemannian geometry, you'd normally work with a unit conormal, or perhaps a conormal of length -1 if it was time-like. So correspondingly here, we work with weighted conormal. So the n conormal will have weight 1. And then with the conformal metric, it'll have length ±1. So you can see why you need the weight then, because the inverse conformal metric is weight -2. So our normals would that's what we'll mean when we have a conormal. Okay, now we're going to use the tractor connection to help understand these things, and that's not surprising. So the tractor connection has been mentioned in several talks. It's the sort of induced bundle version of the Cartan connection. And the usual way I introduce it is I say that on a conformal manifold, you don't have a conformally invariant connection on the tangent bundle, but you do on a slightly higher rank bundle, and that's the tractor bundle. Okay, so again, this was mentioned in previous talks. Here's the tractor bundle. These are semi-direct sums indicating there's some kind of filtration structure. So what this means is the standard tractor bundle has a line bundle as a sub-bundle, and it's the line bundle densities of weight -1. When you quotient by that, then the remaining vector bundle has the cotangent bundle as a sub-bundle. Well, that twisted with densities of weight 1. Okay, and when you quotient by that, you've got densities of weight 1. So that's what that filtration structure means. There's a very special tractor that we call the canonical tractor or the position tractor, which it gives you the injection of that line bundle into the tractor bundle. So that sort of determines the filtration structure. When you pick a metric from the conformal class, this filtration splits and you get a direct sum of vector bundles. And in that setting, it's easy to define or to write down how the tractor connection looks. So here it is given on sigma mu rho. These are coming from the respective summands here. And it's just basically a simple formula, the Levi-Civita connection on sigma minus mu in the top slot, the Levi-Civita connection on mu, plus a bit of the Schouten tensor, plus a trace correction, and so on. So the Schouten tensor has been mentioned in a few talks. It's a trace adjustment of the Ricci tensor. Just think of it as roughly Ricci if you don't know the details. Okay, so the main point of that doesn't matter about the details, but there is a simple formula. And also this tractor connection preserves a tractor metric. So if your original metric had signature PQ, this has signature P plus 1, Q plus 1. And again, I'm giving the formula for the tractor metric as a quadratic form here. So this is conformally invariant, this metric, and preserved by that connection. So in conformal geometry with this stuff, you start to get a sort of setup that's a bit reminiscent of Riemannian Ricci calculus surrounding the Levi-Civita connection. Okay, so in the basic starter pack for conformal geometry, which is what I'm trying to give you, there's also another very useful basic ingredient, which was known to Tracy Yerkes Thomas, that Mike mentioned. This is the Thomas D operator. So if you start with just a density F, then it's landing in tractors with weight just reduced by 1. And here are the 3 slots of the tractors referring to this, the bundle structure up there. In the top slot, it's just some numbers times the function you started with. In the next slot, it's some number here times the derivative with the Levi-Civita connection. And in the bottom slot, a Laplacian type operator. Here, J is just the trace of the Schouten tensor. Okay, now this is on densities, but actually, if instead of taking the Levi-Civita connection and here you take the tractor connection, this Thomas D operator can then act on any weighted tractor bundle. So it gives you an operator that then goes from weighted tractor bundles to weighted tractor bundles. So that's very useful. Okay, so this page here anyway is your sort of basic starter pack for conformal geometry using tractors. So if you like had a student trying to do something, you gave them this, they can already calculate a lot of things. Okay. Now let's go back to hypersurfaces. We want to use that tractor machinery to help us, but let's remind ourselves of some basic Riemannian geometry of hypersurfaces. Okay, so we'll pick a metric in the conformal class. How do you get the second fundamental form? Well, you take your conormal, differentiate it along the hypersurface, but restrict to, so, you differentiate it in directions along the hypersurface. So you're really taking the extension of n off, differentiating it, but then restricting to the tangent bundle to the hypersurface. So, so this object restricted to the tangent bundle to the hypersurface gives you the second fundamental form. Now, to write things down, I will embed the cotangent bundle in the ambient cotangent bundle by an orthogonal projection. So we'll think of the cotangent bundle as n perp inside the ambient cotangent bundle. And when you do this, you get a formula for the second fundamental form that looks like that. Anyway, it doesn't matter, this is a simple formula. But when you write something like that down, we can then work out what happens when we change the metric conformally. So to get the second fundamental form, I picked a metric. Now I changed the metric conformally, and here comes my usual convention for rescaling. I'm going to do it by e to the 2 omega, where omega is any smooth function. Then the second fundamental form transforms like that. Okay, so upsilon here, this cactus-looking thing is just d of omega, so d of that omega. That was the same notation as used by Mike. And what you see here is that the second fundamental form is transforming by just a trace term. So the trace-free part of the second fundamental form is conformally invariant. So that's nice, right? We have some progress already. We've just discovered a conformal invariant of hypersurfaces, the trace-free second fundamental form, which of course is well known. Here, H is the mean curvature. That's my convention for that. And as usual, we're using the weighted quantities to write these things down. So it has a weight. So the this trace-free second fundamental form is weight 1. This is weight -1. And H is not conformally invariant. So, but anyway, the trace-free part is. Now, from this formula, you can also work out how the trace transforms, how H transforms, right? And that's, you can just read it off from here, because the only thing that this, this is the H is giving you the trace part, and this thing transforms by trace. So it's easy to see, as given on this next slide, that when you change the metric conformally like that, the mean curvature transforms in this very simple way. It has a linear amount of upsilon added. So that this is the, remember this is the D of the conformal factor, conformal rescaling function. And so it's just the normal contracted into that. That's the way the mean curvature transforms. At least here I'm thinking of this as a weighted mean curvature. Otherwise you'll get also a scalar factor out the front. Okay, but from this formula, you can see that this object here, this triple, actually is a well-defined tractor along the hypersurface, because the tractors are characterized, when you give them in slots, whether they're invariant or not is characterized by how they transform. And I think this was mentioned in a couple of the previous talks. And I'm not going to go into that, but with the 0 in the top slot, the right way for the thing in the bottom slot to transform is by minus the middle slot contracted into upsilon. And so if we put minus H there, it's exactly going to do that. So this is an invariant tractor. And I'll put these double exclamation marks because I want you to be excited at this point. This is a very good object. I mean, for a start, it's very simple, right? So it's just a tractor made almost entirely out of the conormal. This is an observation made, a long time ago in this original article with Bailey and Eastwood. But it gives us a tractor equivalent of the conormal. Okay, so we can play good games with that because it's conformally invariant. Namely, we can use all that conformally invariant tractor machinery. So this is called the normal tractor. And here's the first result. So if we differentiate this thing tangentially along the hypersurface using the ambient tractor connection, right? So obviously we can do that. This is a tractor. It actually has weight 0, so it's a genuine tractor. And so when we operate with the tractor connection, we get an invariant answer. And if you just differentiate tangentially along the hypersurface, this is what you get. You get 0 again in the top slot. You get the trace-free second fundamental form in the bottom slot, and then just the divergence of that in the bottom slot. So it's just a prolongation of the trace-free second fundamental form. Okay, so this we call the, for example, the conformal shape operator. I'm not sure if we ever completely fix names to these things, but that's one thing to call that. Now, what that means, just reading off from this, is that the hypersurface is totally umbilic if and only if this normal tractor is parallel along the hypersurface. So remember, totally umbilic means that the trace-free second fundamental forms vanishes. So in Euclidean space, that means that it's locally sphere-like, right, when that happens. So in curve settings, it's sort of doing its best to be like that. But this is already a very nice result. Okay, let's continue with our basic hypersurface geometry. The way you get going in Riemannian hypersurface theory, you know, apart from the second fundamental form, which we've already defined, is its use in this thing called the Gauss formula. So let's remember this. So I'm claiming here this is the basis of pseudo-Riemannian hypersurface calculus. So here you have the Levi-Civita connection acting on a vector, but this line under the Levi-Civita connection means I'm only going to act along my hypersurface. So in other words, I'm going to restrict this Levi-Civita connection to vector fields or vectors that are tangent to the hypersurface. That's what the underscore means. The nabla with the line above it is the intrinsic Levi-Civita connection. So that's the Levi-Civita connection from the induced metric in the hypersurface. So we're taking a vector here, which is tangent to the hypersurface, a vector field V, so we can differentiate it with the intrinsic one. And the difference between these is given by the second fundamental form according to this Gauss formula. Okay, so just as I've written it. In fact, this is often how the second fundamental form is even defined using this formula. So once you have that, you can start to compute curvatures and link the ambient curvature to the hypersurface curvature and all sorts of formulae like that, so the Cardazzi formula and so on. Okay, so we would like, this is an important object, we would like a conformal analog of that, a conformally invariant replacement for this Gauss formula. Now we're going to do this via tractors, but notice here that an important thing that we used is that the tangent bundle to the hypersurface just sits as a sub-bundle in the tangent bundle to the ambient manifold, right? Just sort of innocuous there, but that we've really used that. To do this with tractors, we would need to know that what is the link between the intrinsic tractor bundle, because remember, on our hypersurface, we're going to get induced a conformal structure, so it will have its own tractor connection and tractor bundle and so on. But what has that got to do with the ambient conformal tractor bundle? So we need to sort that out first. Now, it turns out that this is quite easy. Along the hypersurface, you can look at n-perp, namely, you can look at the sub-bundle of the ambient tractor bundle that consists of tractors orthogonal to the normal tractor. That's what I mean by n-perp. So this sits inside the ambient tractor bundle along your hypersurface. Now that has the same rank, it's easy to see, as the standard tractor bundle of the induced conformal structure on your hypersurface. So you might hope that these are the same, and indeed there's a natural isomorphism, and I'm giving the details of this down below here. So if you calculate in a scale on the ambient manifold, the tractor bundle, and so n-perp decomposes into a triple, And then the isomorphism is just given explicitly here. So here, sigma, mu, and rho have to satisfy that they're orthogonal to n. So this is in this, the perp of the normal tractor. And then you simply map that triple to the triple over here, and this gives you a intrinsic tractor bundle triple. So this then transforms correctly that way. And you can see that the mean curvature is appearing. So I mean, this is the most obvious thing. In other words, sigma, mu, and rho again, except the mean curvature is there. Now you can pick a distinguished conformal metric from the conformal class so that H vanishes. There's a class of such distinguished metrics. So when you're given a hypersurface, you can restrict to metrics in the conformal class that have H0, and then the triples map across in the most obvious way, which is what was stated in this article with Branson, that if you work in that scale, which is, it's easy to see there is such a scale, then things map across in the right way. And then later I had a student write out those details. Okay, so now we've got the basics set up to have a type of Gauss formula. So now we have two connections on the intrinsic tractor bundle, which henceforth we're going to identify with this n-perp. So we'll just think of the intrinsic tractor bundle to the hypersurface as being the same as n-perp because we can identify it. But now we have two connections, namely we have the intrinsic tractor connection of this thing, because on the hypersurface it has an induced conformal structure, it has its induced tractor bundle, and it has its induced tractor connection. But you also have the ambient tractor connection, and so you can make a projection of that ambient tractor connection. So this is just the usual thing that you do by orthogonal projection. So you take a tractor field in the n-perp, differentiate it with the ambient tractor connection in the directions along the hypersurface, and then project the answer back orthogonally into n-perp, right? So I'm calling that nabla tilde. So you have that connection and the intrinsic one, and they both act on these bundles we're identifying now. So then you can use that to compute the difference between all these things, and here's the answer. So the ambient tractor connection differentiating tangentially gives you the intrinsic tractor connection plus this S term, and here was this tractor second fundamental form, the shape operator. Now these two bits here, the first two bits, those are just this projected tractor connection. So that's how it works. So the Gauss formula is like the usual one where it's just the shape operator showing up, or the second fundamental form, but it's a tractor version. But then the projected tractor connection is not the same as the intrinsic one, and it differs by this S object. And what this S is, so it's a tractor, but it's really incorporating just, the only content in it is a known conformally invariant that was known to Fialkov. So we now call this the Fialkov tensor. Okay, so I've written down one explicit formula for it. It can also be written as sort of the difference between the Schouten tensor on the submanifold versus the ambient Schouten tensor. And it looks more mysterious then, but when written like this, it's obviously conformally invariant. So this gives us the basic machinery now to link the intrinsic tractor connection to the ambient one, and so on. So you can see we're building up a hypersurface calculus. Now let's pause for a minute to sort of celebrate and do something. So remember, one of our aims was to produce invariants of hypersurfaces. So I now claim you can produce lots of them. You can proliferate them. So we need a proliferation treaty or something like that. So on a hypersurface embedded in a conformal manifold, we have this normal tractor, which remember I was excited about and trying to get you excited about. So we can form something else, namely we can do a Thomas D type thing to that normal tractor. And this produces something that we sometimes call the tractor second fundamental form, but it doesn't matter what we call it. You can do this. So what is this D bar here? Well, it's basically that Thomas D operator I mentioned, but I'm using the Thomas D of the formula for the hypersurface tractors, right? So think of the formula you'd write down for the hypersurface Thomas-D for its intrinsic conformal structure, except I'm coupling it, inside it, I'm using the ambient tractor connection, right? So if you do all that, then you get a well-defined operator like that you can differentiate. So this differentiates only in directions along the hypersurface, but it's able to deal with ambient tractors, right? So you can do that. And in fact, you can keep doing it, right? So really you would use here, for instance, coupled intrinsic ambient tractor connections and so on inside these D bars, but you can iterate these things and take multiple D derivatives of this normal tractor. And everything you're doing is manifestly conformally invariant. And you can contract them together to get scalar conformal invariants and so on. So this is a way you just manufacture things. And these will be typically horribly complicated. I mean, they'll have thousands of terms, but because you're building them in this way, it looks just super easy. Now I'm going to call these easy invariants. So as I say, if you were doing these some other way, they might look very difficult to get these objects, but this just spits them out. But it doesn't make some of the most interesting ones. So there's always these certain critical weights where the objects are exactly the right weight to integrate on your manifold and so on, and then they turn out to be the weights where it's hard to get them. And that's true here too. So we'll talk about some more interesting invariants in tomorrow's lecture and then the one on Wednesday. But this is at least gets you off to a start. If you're trying to make all invariants of hypersurfaces, this is a damn good start. Right, let me say that. Okay, but now I want to turn to another application because I talked about making operators, differential operators and so on along a hypersurface. So let's turn to another type of problem. So consider a conformal manifold with boundary. Maybe this is a Poincaré-Einstein manifold. So remember, a conformally compact manifold, we can think of it as a conformal manifold with boundary. It just has more structure. But you could forget about that more structure and think of it as such a thing. So this is a good setting. So we're interested in conformal manifolds with boundary. So at the moment, we'll just assume that this is a conformal manifold with boundary. Now, there's a way to make a conformally invariant Dirichlet-to-Robin operator. So you no doubt know about the usual Riemannian Dirichlet-to-Robin operator, but you can make a conformally invariant one as follows. So start with a function on the boundary, or really a density of weight 1 minus d over 2. So d is the dimension of the bulk, the interior. And then try and solve this problem. So here is the Yamabe operator that was mentioned in Mike Eastwood's talk. So this is the ordinary Riemannian type Laplacian. If you add this amount of scalar curvature, then you get a conformally invariant operator. Now on the boundary, we have to be careful. So we could form this sort of Neumann type operator, but hang on, no, we can't because this is a conformal manifold, so we don't have a Levi-Sever connection. But if we pick one from the conformal class, we can write down this thing, and it turns out to be conformally invariant. So here we've added an appropriate amount of the mean curvature. In this case, for this problem, it's going to be 1 over d minus 2 amount, but this is conformally invariant on any weight w with that formula. So this is the conformally invariant Robin operator, or the Cheria-Robin operator. Robin just means it's a mixture of Dirichlet and Neumann, but in a sense, you should think of this as mainly Neumann, because there are scales that make H0 and so on. Okay, but anyway, that's conformally invariant. So what you can do is you can start with your density on the boundary, use it as boundary data for this Dirichlet problem, which is conformally invariant, and then apply this delta 1 to the answer and restrict to the boundary. That's really only defined it on the boundary, so you have to. But so then you've done so the map from F, original boundary data, to this sort of Neumann or Robin data is then the conformal to Robin operator. And by construction, this is conformally invariant, and it's well defined provided this original Dirichlet problem has a unique solution, which generically it will. I mean, there can be geometries and situations where it won't, but you know, people put that in usually as a restriction. They just ask it to have a unique solution. Okay, well, here's a question before I go on. Can we make more things like this? Is this the only game you can play in town? Certainly we have analogues of this Yamabe operator. These are the GJMS operators that Mike mentioned. There's the Panizzi operator that's Laplacian squared plus lower order terms. Then there's operators that have Laplacian cubed plus lower order terms and so on. So we have things to play the game for the interior operator at higher order. But what about this boundary Robin operator? Can we make analogues of that? So that's what I want to talk about now. And then the application of it. Checking time. Okay, so first of all, there's a way to do this quite naively. And so what I'm going to talk about now is just going to look like a sort of mainly an obvious application of tractor calculus and so on. But I want you to pay a bit of attention, because tomorrow when I talk about things, connecting more with Andy's talk about holonomy reduction and so on, we'll see that we can come to similar things from a very remarkable perspective. Anyway, let's proceed naively at the moment, because we've got this sort of kit, our basic tractor kit. So in Riemannian geometry, the basic Neumann operator is, you would take, for instance, the Levi-Civita connection and just contract in the normal. Okay, so we'd say this has transverse order 1 for obvious reasons, right? Differentiates 1 off the boundary direction. Or you could do 2 ends into 2 derivatives of the Levi-Civita connection that would have transverse order 2 and so on. So we know how to do these things in Riemannian geometry. What about in conformal geometry? So we want to make analogues. Now, the tractor tools above suggest an immediate game. Namely, we have this normal tractor, we have the Thomas D. So we can just do a kind of Lego maneuver and contract these together, like I've done in this box down here. And actually, if you do that most obvious thing, then at almost all weights, you recover this Robin operator that I mentioned already, this conformally invariant Robin operator. So it just automatically produces it. Okay, so then there's a very obvious then move. You go, well, that worked well, so I will just do the obvious thing. I will take lots of Ds. I will follow with this Robin operator and contract in a whole lot of normal tractors. And indeed, this basically works. So it constructs a family of conformally invariant, obviously by construction, hypersurface operators along your hypersurface. This is very obvious. This is what I call a naive construction. Now, let's try and be careful now. So it would appear, when you write down this formula, that this thing's going to have very high transverse order, right? Because of all these dots and these Ds, you know, surely this is going to have very high transverse order, a lot of derivatives off the hypersurface. And you would think at least it's always 1, right? Because you've got this delta 1 sitting here. You'd think that's really safe. But actually that's wrong. Whoops, what's happened here? I just never click at the wrong time. Right, this is wrong. So let's look. When you take the one of 2, right? So that will just have delta 1 and 1D and then 1N, right? So that forms delta 2. Now, if you use the weight, which I call the boundary Yamabe weight. So this is the weight at which the boundary Yamabe operator is conformally invariant. Then this delta 2 actually just is the boundary Yamabe operator. Well, also a bit of the second fundamental form contracted, trace-free second fundamental form contracted into itself, but that's just conformally invariant. Just forget that. This is the boundary Yamabe operator. So at that weight, this operator has transverse order 0. So if we wanted to make, that it completely failed that test. On the other hand, it produced something very interesting, a boundary conformal operator. Now, so at this weight, it's got order 0. What about if we replace this weight with the interior Yamabe weight? So that'd be 1 minus D over 2. Remember, D is n plus 1. Then this operator, by the same general formula, turns into the interior Yamabe operator, which is conformally invariant, and does have transverse order 2. So we see that there's quite a lot to understand with what's going on with these things. We can't just use them naively, but there's also kind of good, because interesting things are turning up, and that's a whole story that I'm not really going to go into. It's, for instance, Andreas Juhl has looked at analogous things where these special things happen at special weights and so on. So anyway, those things could be viewed as treasures because interesting things turned up, but bad things, really bad things happen. Namely, for instance, if you look at delta 3 at this Panizzi weight, so this is the weight for the interior Panizzi operator to be conformally invariant, delta 3 is just 0. Well, at least it is in the conformally flat case. I think it probably is in general, but it certainly is in the conformally flat case. And that's obviously bad. 0 is not interesting no matter what. Okay, so how do we fix this? Well, what you can do is you can, with sufficient cunning, and even in the conformally flat case, it's not completely trivial, but you can use an induction to prove that, because what we want to get is a lot of normal derivatives, right? So transverse derivatives like that. And if you compute these delta k's, you can show that you have this product of numbers times the sort of maximal number of normal derivatives. This is the most it can be for this delta k, plus lower transverse order terms, right? So we're interested in when this leading term survives. And the bad weights is when it doesn't. And there's a big list of bad weights. So if anything in this product is 0, then we're at a bad weight. So there's a lot of bad weights, it turns out. However, on conformally flat manifolds, we can actually improve things a lot. So it turns out that pretty much on the nose, you can get rid of every second one of those bad weights. So in other words, if we go back, there's all these factors here, but some of these factors are factors for the whole operator, so that these lower transverse order terms, they also have this factor in. So then you can take it out. So that's what we're doing on the next slide. So what you can show is that you get a formula like this. So there's a collection of weights for which the factor comes right out. And so this delta k that we made naively is just some number, if you like, or some polynomial in the dimension and the weight times an operator. And so you can just cross that off, and this thing will then still work and be conformally invariant. This is by polynomial continuation in the weight, but it's easy to show that that will be conformally invariant even at the weights for which that was 0, right? So this is a way of producing something, and this is not, there's nothing spurious about this. You can really prove that this is then conformally invariant. Okay, so you can reduce the number of bad weights considerably, and I've got in a box an important case down here, but I won't have time to really discuss. But for instance, that Panizzi weight one, that delta 3 that made that 0, that doesn't happen after you've done this trick, right? So you get something. So let me, just before I finish up, give you an idea how to do the proof of that, because it's, again, not completely trivial, but what it uses is that when we go to something like, here's this Panizzi weight, this T phi means any tractor bundle of that weight, then if you take a section of that and you do 2 Thomas D's on it, then at that weight, in the conformally flat case, this 2 Thomas D's just has to produce the Panizzi operator in the bottom slot, and 0 is above it. This is just by basic invariant theory, because there are no conformally invariant operators landing in these, that can land in these places. I mean, this really happens by calculation, but you can also just see it's going to happen. So now, because everything is polynomial in the dimension and the weight in a way that you can define, you use a sort of basis of invariants and operators. That means that when you write this down at other weights, and at a sort of general weight and dimension, there must be this factor d plus 2w minus 4 in all of these places where the zeros were, right? Because of the polynomiality. And similarly, for instance, if we do the 3rd order one, so with the 3Ds, you'll get a P6. This is a 6th order GJMS operator in the bottom slot, and 0 is above. That has to happen at the right way. So you can conclude that when you go to other weights, you have to have these polynomial factors. And then, it's not too hard to show that these factors survive when you make the formulas for those delta Ks by contracting the ends in and everything. And that's how you eventually prove what I claimed on the previous slide. Okay, but what about the curved case that's conformally flat? Well, I'm not going to do this in detail. If you do DDD on F, well, the 2Ds just still works, but if you do 3Ds, then you get a big mess, right? So first of all, it looks hopeless that you can play this game at all. But in fact, using some earlier work that was kind of unrelated to this problem, we already knew how to get rid of that mess. So because we were interested in the past in producing GJMS operators in the curved case, so we know how to modify this to a better operator so we again get the zeros. We still have the polynomiality, questionably spelled there, but you can play the same game. But you have to be much more careful, and it's sort of, it's more complicated, but you do get a result. So in the end, in this recent work with Peterson that's appearing in Pacific, I think it's, as I say, I think it's already on the MathSciNet, we produced what I think is perhaps an optimal construction of higher order conformal Raban operators. So there's the first order one, which is the usual Raban operator, the second order, and so on. And there's different things happen in different dimension parities and so on. The story is complicated. I don't want to go into it, but you get a sort of optimal answer, I would claim. And here's the application. So, for instance, now we can use this GJMS operator of order 2K as the interior operator for a Dirichlet-Neumann type construction, but a conformally invariant one. So you take these boundary operators that Peterson and I made, and you suppose that the Dirichlet problem with these is the sort of generalized Dirichlet boundary operators, and your higher GJMS is the internal one. You suppose that as trivial kernel. That's a sort of standard, restrictive assumption, because it, as I say, and generically it will have trivial kernel by ellipticity and so on, but it can have non-trivial kernel in specific cases. But then you get a well-defined Dirichlet-Neumann by just solving the problem with this boundary data, and then taking one of the higher order boundary operators and applying it to the answer and restricting back to the boundary. And what this is saying down here is the way you really do this in practice to get sort of nice answers. You're solving this interior GJMS U equals 0 problem. You set most of these deltas on your function to be 0, so nearly all 0, but you prescribe one of them. So one of these, the delta L1 on that's your prescribed boundary function, and then all the others you take to be 0, and then you solve the problem, and then you spit back to the boundary with one of the other operators. Okay, and then what you can show is that these give these powers of the square root of the Laplacian. I mean, at leading order, these things are powers of the square root of the Laplacian. So this is a non-local operator. So of course, this has strong links to the idea of scattering, if you already know about scattering. So this is a kind of alternative. So you might do scattering with similar things, and in some cases, this would coincide completely with what you're getting from scattering. And I'll talk about scattering briefly tomorrow. Just before I really finish, just to mention something that you perhaps haven't heard about, which I call T curvatures. I'm not going to get to talk much about Q curvatures today. I'll mention it in the last talk now, actually, I think. But there's an old idea that I'm attributing to Branson here, but I think really it came from physics. So if you have a Riemannian differential operator given by a formula where when you write it as a Riemannian operator, it depends polynomially on the weight in this sort of way. So you have an operator which acts on things of all weights. I mean, it's going to be conformally invariant, right? So I'm going to ask this thing to be conformally invariant. But when you write it out as a Riemannian operator, it has this form. It's some part of the operator that, composed with the Levi-Civita connection, plus the weight, because this depends on the weight, times another part, which also depends on the weight. Okay, so if you have a formula like that, then there's a general argument that if you pull off this bit here, so you take this Q that's the coefficient of W, and you set W equals to 0 in there, then that will transform conformally like a Q curvature, right? So the Q curvature does this, but the argument that leads to this transformation is just general. It doesn't just apply to the Q curvature. You just need this situation. So in particular, you could ask that you played this game. So the operators that Peterson and I made actually have this form, right? So they do have this form. And so we call it a T curvature if this thing that transforms this operator 0, right, this Q-like thing that we're going to call a T curvature, if this bit here that acts linearly on the rescaling factor, so I'm now unfortunately changed to e to the 2 epsilon, sorry to be confusing, I was using omega before. So if that has the maximum transverse order, then depending, relative to some weights, we call that a T curvature. Right now, so those operators that we produce have that property, so we can manufacture these T curvatures. And this is interesting because T curvatures turn up as transgression terms in conformal anomaly calculations. So that's really the original motivation, although it's already interesting like this, I think. And we give one other application of this, but yeah, so they turn up in interesting places. So here's an example result. So I'm almost about to stop. So for instance, on odd dimensional interiors, so you have a hypersurface of a Riemannian manifold, and suppose that the dimension of the interior is even, so the boundary is odd dimensional. Then you can make these operators and T pairs up to all orders, right? They just go on forever. So, and each one of them transforms like that. So the T curvatures transform, in fact, exactly, so I'm not writing it as a density now, I'll put that factor out the front. So the mean curvature transforms like this. So these are higher, if you like, higher order analogues of the mean curvature. So remember, the mean curvature transforms to be itself plus the normal differentiating the conformal factor. So these transform the same way, but with higher order. So, and as I say, these things turn up as transgression terms, meaning boundary terms in things like the integral of Q curvature and so on. Okay, so what's the time? Yeah, so I started 2 minutes late, but I can stop here. I do have a couple of other things to say if people want, including some examples, but I can stop there. So it's probably enough.
Thank you very much for the lecture. Are there any questions? Please.
So you showed several ways to produce families of conformal invariant operators for boundary calculus. Is there any claim of completeness of this?
No, I mean, it's okay. It's very hard to even define what you mean by complete. So for instance, with the boundary invariants, as I mentioned, I would say at this stage, we do not know how to make all invariants of hypersurfaces. At least we don't know that we know. The reason is that, as perhaps mentioned in Mike Eastwood's talk, we don't even know how on even dimensional manifolds to make all conformal invariants, just of a general conformal even dimensional manifold. We know how to make almost all of them though, so there's a small window, and it will be the same for hypersurfaces. Now for invariant operators, it would be a sort of similar story. If you restrict things, do you mean invariant operators tangential to the hypersurface? Do you mean operators like these ones I'm making with Peterson, which are kind of transverse to the hypersurface, or some mixtures of them? It's extremely combinatorially complex to even define what category you want. But in any sort of, if you restrict it down and say, okay, I want things of order no higher than this and blah, 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 then in practice, we probably can make them all. But really proving that you can make them all is a complicated problem. Yeah.